Danilo is giving the talk. Danilo, you have 20 minutes, 18 plus 2.
Thank you for the introduction. So I'm going to talk about proof of replication. But before we start, I'm going to start talking about an earlier primitive, proof of space, that was being proposed to replace proof of work and the time to compute the proof with space. And in proof of space, you usually send a seed to the prover that is going to expand the seed by producing some random blocks. And this is done by pebbling an hard-to-pebble graph, so it's a very slow process. And after you expand this seed, you store the blocks and you commit over the blocks, and later you can receive a challenge and you can produce a proof only if you store the majority of those blocks. And this has been proposed to replace proof of work, and a key point of proof of space is that usually the expansion is low because otherwise you may restart the expansion when you need to produce a challenge, and you may produce a proof without storing any data persistently. And the problem of proof of space is that we don't store any useful data, so you simply store like random garbage. That's why we have proof of replication. So you have some data that comes from an untrusted party, so you don't know anything about the data, could be all zeros. And we want the prover to force and use some space to store this data, even if the data is compressible. And this is done similar to proof of space. Usually you pebble a graph, you compute a random encoding of the data, and you commit over the random encoding. And then later you have a challenge, and you receive a challenge, and you can produce a proof only if you store the majority of the random encoding. And this is very nice because we can build decentralized storage systems, and that is now used by Python for this purpose. So we have some algorithms when we talk about proof of replication, and they are divided according to the preprocessing, so the encoding and the audit phase. We have a setup that generates some encoding keys, some keys, so an encoding key, a proving key, and a verification key, they're all public. And then you have an encoding algorithm that takes the data and some identifier and produce the random encoding and a digest. And then later in the audit phase, you can check that you're storing the random encoding by simply sending a challenge, and then the prover is going to run this proof algorithm that takes in input the encoding to produce a proof. And then you can verify, of course, the proof, and you can also decode the encoding when you need to retrieve the data. Proof of replication needs to satisfy some properties, but the most interesting one are replication extraction. So extraction means that you actually storing the original data, the useful data, and you can extract it. And in replication, you essentially want to prove that you are using a significant amount of memory in storing the data, even if it was compressible. And that's the property I'm going to talk about in this presentation. So the space property of proof of replication is like a combination of different primitives at a very high level, at least, from like proof of space, probability of possession, and proof of replication, because we get a lower bound in the memory you need to use from proof of space. And then from PDP and power, we get the fact that you are storing useful data and you can extract this data. So you can retrieve back this data. And as I told you before, in proof of replication, it's mandatory to have a slow encoding, because since the data is completely malicious, you may compress the data, and in order to compute a proof, you don't need to store the data, you simply run the encoding and then compute the proof. But to avoid this problem, you have an encoding that is slow, and you ask the prover to give you back a proof within a certain time window that is smaller than the running time of the encoding, so that you know that if you pass verification, you haven't run the encoding from scratch, and you're using some memory. I'm going to talk about the construction of fish to see what we would like to improve from this construction. That's the objective of our work. So in fish, what you do, you get some data, and you start to pebble using the random oracle a depth robust graph. You start pebbling, and you obtain the labels of the last layer of this graph, and then you take these random labels that are blocks, essentially you XOR with the blocks of the data, and now the output of this XOR is simply the encoding. You commit over these blocks, using like a Merkle tree, and you're done. And let's assume that the setup is done honestly. Now, if you try to cheat later, and to check that you're using memory, you simply select some indexes, superlative number of indexes, and then to pass verification, you need to provide me back the labels of the encoding, the blocks of the encoding, and the Merkle tree openings. And with this strategy, you can prove essentially that you can pass verification only if you store 1 minus epsilon, the 1 minus epsilon fraction of the blocks, where epsilon is a constant. And this is nice, but the problem is that in proof of replication, you want usually to store multiple files, because you may have a lot of memory. And now if you have like multiple files, let's say you have that the loss, the epsilon, is going to scale with the number of files. So the more the file you store, the more memory you may save. And that's not so good, so we would like to solve this problem. And actually, in Fish, you can solve this problem by increasing the number of challenges, the indexes of the challenge phase. But that's not something that you can always do, because you may not either know in advance the number of files, and you need to increase the challenges proportional to this parameter. And also, if you scale this parameter, you may slow the entire proving procedure, and you may end up in really like the majority of the memory. And we want to have something that is like efficient, sublinear, hopefully, and also a proving strategy that provides you a better memory bound in terms of user and doesn't have this loss that scales with the number of files. So in our work, we propose a construction with these properties. And for simplicity, we assume that encoding is always run honestly. So the digest of the encoding is always computed honestly, because in the worst case, you can snark it and you don't have any constraint in time, so you can do it. And now using this correct digest, we want to define a different strategy improving the usage space so that it's efficient and you get a memory bound that doesn't have a loss proportion to the number of files. So I'm going to build the construction step by step. And the first ingredient is polynomial evaluation. So you get a random polynomial, and the setting is that you receive a random challenge, and now we ask the prover to compute f of x, and we want to measure how much space you need to use to do this task. And intuitively, since the polynomial is random, you need to use some memory that is proportional to the size of the polynomial, and this should hold even if you try to preprocess the polynomial in some way, in some arbitrary way to save memory later. And it has been shown that the memory that you need to use is, in case of preprocessing, is the size of the polynomial minus a loss, where the loss is the degree of the polynomial times the size of the challenge, so the random point. And the reason of this loss is because a prover may preprocess the polynomial in such a way that it's going to answer only of those challenges. So the point, they share some bits with the coefficients of the polynomial, and now you have this loss because you have d coefficients, so you have such a loss. So that's bad because we still have a loss that may scale with you. So we analyze in our work, we analyze what happens when you have u polynomials, for each file, for example. And what we show is that if I challenge all the polynomials on the same point, we get that the loss doesn't scale with the number of files, so it remains constant. So when you have u files, we get that the memory you need to use to provide me the evaluation of all the polynomials is the size of the u polynomials minus the loss as before that doesn't scale with u. So for very large value of u, we are kind of happy because you don't save such much memory. So the partial construction may look like the following. So if you are storing 2 files, you parable the graph as before, you XOR with the data, you get the encoding, and now you read the encoding like a polynomial. And then later in the audit phase, you can simply send a random point, and the prover needs to compute f of x. Using this approach, we're gonna inherit the memory bound that I told you before that scales with the number of files in a nice way. But the problem is that to use this technique, we need to solve these 2 problems. One, the current construction requires reading all the coefficients. So you're going to read the entire memory when you want to provide a proof, and that's something we want to avoid. And also, you need to find a way to verify that f of x is computed correctly, because otherwise you cannot claim anything about the security. So to solve this problem, the first problem, it's kind of easy, let's say, because Kesaya Human has proposed a data structure that in the RAM model. So essentially, you can take the polynomial, you preprocess it. You don't store the polynomial in plain, so you store the data structure. And now the data structure allows you to compute f of x in time polylogarithmic in the degree, and the degree is also the number of blocks that you want to store. So it's sublinear, and we're happy. So now we solved the first problem. We need to solve the second one. So a naive approach will be to use a snark. So you can prove that f of x is computed correctly according to the data structure. But this doesn't work because we are using the data structure to be efficient. And to prove that the computation has been done correctly, you have essentially that the data structure is the witness, and it's going to be the computation of the proof is going to be linear in the data structure. So we completely defeat the running time of the efficient running time of the data structure. So the observation to have an efficient verification in this case is that the computation of f of x is already efficient. So to have an efficient verification, we may simply ask the verifier to run the same computation, but the verifier doesn't have the data structure, so it cannot. But the observation is that it doesn't need the entire data structure because it's in the RAM model, the data structure. So if your running time is polylogarithmic, it means that you're going to read only a polylogarithmic number of blocks, and you can send only those blocks to the verifier. And that's essentially the solution, because in the preprocessing, when you encode the file, also you're going to commit over the blocks of the data structure using a Merkle tree. This is done honestly, as I told you before, so you're going to publish the digest now. And for verification, and for the audit phase, you're going to get a random point. The prover is going to read some blocks. And as a proof, it's going to send back f of x, the blocks read, and the Merkle tree openings. Now, assuming that the digest is honest, what you do, you simply check that the Merkle tree openings are correct. So now that you know that the blocks are the correct blocks of the data structure. You can compute y using these blocks, and then you can compare simply y with f of x. And that's the verification. So if we combine all these ingredients together, the final code structure looks like the following. And in the paper, we use a modular black box approach, but this is the construction when you open those boxes by using the technique also of fish. You essentially get some data. You compute the pebbling using the random oracle. You take the last layer. You XOR it with the data. And you obtain a polynomial. You don't store the polynomial in plain, but you compute the data structure. Now that you have this data structure, you commit over the blocks of the data structure, and you publish the digest. And now in the audit phase, you get x, and you compute the proof as before, as I told you before. And you can check the computation, as I said. So you check the Merkle tree openings, you compute y from the blocks read, and you compare the two outputs. And we get the fact that we are using, at the core of this construction, we use polynomial evaluation. So you get this bound u times the size of the polynomial that is also the size of the original data. And that scales well with the number of files. And also we get proving a verification time that is sublinear, and in particular polylogarithm in the size of the file. So that's the construction, and I would like to conclude the talk by showing you some limitation of the construction, which essentially makes the fish construction or construction comparable. So this is the size of storing U files. In fish, it's proven that a malicious strategy is going to use a 1 minus epsilon fraction of those memory. So it's here. You have this loss that scales with the number of files. And in our case, where the bound is much higher because the loss doesn't scale with the number of files. So in this case, in terms of absolute memory use, we are better. Because the malicious strategy requires more memory than the one of fish. But also, another metric to measure the space used by the malicious prover is to compare the malicious strategy with the memory of an honest party. So in this case, in fish, the honest party, we need simply to store the encodings plus some Merkle tree openings that is essentially just scales with, just doubles the memory. So asymptotically is here, the honest strategy. But in our case, we store the data structure, and the data structure has an expansion. So when you preprocess the polynomial, you are going to increase the size of the data structure, so it's more than the size of the polynomial, and that's because we want to be later efficient in computing f of x. And in particular, the size of the data structure is the delta root of n times larger than the size of a file, where n is essentially the size of the data. So when you compare the true construction using this metric, essentially we are worse because now the malicious strategy and the honest strategy are far away from the one of fish. So an open problem is essentially to take the best of the two constructions, so having something that is efficient, so sublinear, as in both constructions, but we get a higher absolute memory usage like OR construction, and also at the same time a minimized space gap as the one of fish. And yeah, that's the end of my presentation. Thank you. Sorry, what? Yeah, because I mean, it's as I told you before, when you evaluate U polynomials, you get that the memory you're going to use is U times the size of a polynomial, so the size of a polynomial is n, minus something that doesn't scale with the number of files, U. So for large U, that's approximately the size of all the U files. It would? It scales with the loss, you mean? The loss, yes. But that's also for fish, for example, because you have 1 minus epsilon multiplied by n. So the larger the n, the more the loss.
Now we move to the second talk of the session. The title is a formal treatment of end-to-end encrypted cloud storage. This is joint work by Matilda Bakendal, Hannah Davis, Felix Günther, Miro Haller, and Kenny Patterson. And Matilda and Miro are giving the talk, right? Okay. Miro, you have the floor.
All right, good. Thank you very much for the introduction. This is Matilda, I'm Miro, and in this talk we are going to lay the formal foundations for end-to-end encrypted cloud storage. So after motivating why this is an important goal and why it's not trivial to achieve it, we will present our syntax, security notions, and the proofably secure construction for end-to-end encrypted cloud storage. So let's start with the motivation. I'm sure all of you are familiar with cloud storage and possibly use it every day, but let me recap some of the key aspects to make sure we're on the same page. The cloud is a cluster of servers that's accessible over the internet. Moving your data from local storage to the cloud has a lot of benefits. One of them is that you can access the data from any location and any device that you wish. Also, if a local hard disk catches fire, then your data is burnt, unless you have a backup somewhere. But in the cloud, cloud operators handle redundancy for you in a way that makes sure that the end user doesn't even notice a hard disk failure. Moreover, cloud storage can be scaled to hundreds of terabytes without that the user themselves needs to go and install more hard disks. So with all these benefits, it's perhaps not surprising that cloud storage is vastly successful and expected to store 50% of all the world's data by 2025. Big providers include Dropbox, Google Drive, iCloud, and OneDrive. But there are also concerns with cloud storage. Reading data from a local disk means that you need to have physical access to this disk. This is no longer true in cloud storage because data stored in the cloud means it's transferred over the internet and stored and remotely accessible. And so that increases the risk against data confidentiality breaches by external parties. And so what most of the cloud providers do is they implement server-side encryption. That means they encrypt the data at rest with a key that's known to the server to address these issues. However, external adversaries are not the only threat we care about. Data that's uploaded to the cloud can be highly sensitive. For example, it can include healthcare data. And so we also want to consider the case where the cloud provider themselves is compromised or even malicious. And so in that scenario, server-side encryption is no longer secure enough because the server knows the key. But in this case, end-to-end encryption addresses this by encrypting data before it's uploaded to the cloud. And the big providers have started rolling out end-to-end encryption in the last 2 years, but often this feature is still optional, and enabling it limits you in the functionality that you get out of this cloud storage provider. In contrast, there's a lot of smaller providers that offer security as their main selling point and that have end-to-end encryption by default. This includes Mega with over 300 million users and the self-hostable Nextcloud that's used by the German government and many other big organizations. Unfortunately, though, a recent line of work has shown that all of them got end-to-end encryption wrong, and the issues range from smaller things up to full key recovery attacks and plain text recovery attacks. So how is it possible that all of them got end-to-end encryption wrong? It seems at first that you can just simply solve client-side encryption by picking a key on the client and then using your favorite AEAD scheme to encrypt the file before uploading it to the server, right? Then you're already done. Unfortunately, that doesn't work for multiple reasons. The first of them is that if you want to access your file from a different device, then you need to have a way to transfer the key from the device where it was generated to the device where the file is decrypted or should be decrypted. And so in practice, predominantly what's used for this is to derive keys from the password of the user. So one way you could do this is you could have the user type in their password and then directly use that key to encrypt a file. But this, of course, means that the security that you achieve depends on the strength of the password. But there are also more subtle issues, and one of them is if the user wants to change their password, then that means that the key derived from the password also changes. And so this means that the user would need to fetch all of their data from the cloud storage and re-encrypt it with the new key before deleting the old one. Unfortunately, this is prohibitively expensive at the scale of cloud storage. We also have another issue. One of the key aspects of cloud storage is that you are able to share files with other users. But obviously, it's not a good idea to share your account password with another user just for them to be able to receive and decrypt the file. But this is exactly what you would need to do if you derive a key directly from the password. So there's a simple solution to this that cloud storage schemes use. It's just to build a key hierarchy. So instead of directly deriving file keys from the password, we pick them independent for every password. This is good key hygiene, but it also allows us to share access to a single file by sharing the file key with other users. And then those file keys are encrypted with a master key, which itself is encrypted with a key derived from the password. And so now if the user changes their password, we only need to re-encrypt the master key, and we don't need to re-encrypt all the files or the file keys.
Well, so you convinced me at least that end-to-end encrypted cloud storage isn't trivial, and that Mega and the others face several hurdles on their path. But they actually managed to overcome them, mostly. So I think that the bigger problem for all of these providers that tried to implement secure cloud storage was that even after overcoming all of the challenges, they were lost. They didn't really know where they were going. There had been no formalization of secure cloud storage, so the cryptographic goal wasn't clear. Of course, there's been other academic work on cloud storage, but it's either focused on more specific settings, so for example, backups for secure messengers, as we'll see in the next talk, or more advanced security goals, like metadata hiding, allowing a user to revoke their own access, or providing forward security for deleted files. But there was no formalization of the basic security goals for end-to-end encrypted cloud storage. So that's what we set out to change. In this work, we provide the first complete cryptographic model of end-to-end encrypted cloud storage. We also define game-based security notions to capture the expected integrity and confidentiality guarantees against a compromised or malicious cloud storage provider. Finally, we proposed the first provably secure construction, which we named CSS for Cloud Storage Scheme. If anyone has more creative name suggestions, please come find us. So let's have a look at our framework, starting with the syntax. To define the syntax of a cloud storage scheme, we looked at real-world systems and tried to answer the question of what makes a cloud storage scheme a cloud storage scheme. And we extracted the following core functionality, which consists of 7 protocols. The first 2 are registration and authentication. So registration allows a user to set up an account with the service provider, and authentication allows the user to log into its account and start an active session. Now, once logged in, the user can use the following 5 protocols to manage their files. Put to upload a new file, update to modify the content of an existing file, get to download a file, share to share a file with another user, and accept to receive such a share from someone else. Each of these operations is an interactive protocol between a client and the server. Now, with this core functionality, we were able to both capture the essence of a cloud storage scheme and to model real-world systems. But we need more from our model than that. As the British statistician George Fox allegedly said, all models are wrong, but some are useful. So in order to make our model useful, we had to make a bunch of subtle choices. And I'm just going to highlight a few of them here today. So the first one is that our syntax supports non-atomic operations. I said before that each of these protocols is an interaction between a client and a server. But in reality, there's not just one client, but many. And they might all try to interact with the server at the same time. Now, this can lead to concurrency issues, which have to be handled by the server. And in practice, it's not realistic to assume that the cloud server will serialize these operations. So for this reason, similar to in key exchange models, our syntax allows arbitrary interleaving of these protocol messages. So what this means is that if 2 clients try to interact with the server at the same time, the server doesn't have to pick one and run that protocol to completion. Rather, it can respond to the first one and then the second one and so on, arbitrarily interleaving the messages. Now, syntactically supporting non-atomic operations is important because it allows our framework to faithfully capture real-world systems, and therefore also their potential security flaws. Okay, the second model choice that I want to discuss with you today is that we allow the sharing protocol to use an abstract out-of-band channel. So when a user wants to share a file with another user, they have to communicate the key material needed for decryption through some secure channel. In practice, this channel can be instantiated in a variety of different ways. For example, by relying on a public key infrastructure, using a secure messaging, or sharing a password or a link. Now, in our model, we model this as an abstract out-of-band channel without specifying how it's instantiated. And the reason for this is that we want to keep our framework as generic as possible to allow it to capture a wide variety of both existing and future systems. Out of all of the things that I showed you now, the main things that sets our framework apart from related work is the handling of file sharing and the support for non-atomic operations.
So now that we have seen how we can capture cloud storage systems, we can start to formalize what security we would like to achieve for them. For this, we consider a threat model with a malicious cloud provider that has full control over the network and all operations that the users perform. This materializes in the game as follows. We have a set of honest users that run an interactive protocol with the malicious cloud provider. These users have passwords that are sampled from a password distribution, which is parameterizing the game. That means that these passwords can be weak, and they can also be correlated for some of the users. And of course, the bounds that we prove will depend on the password distribution. Moreover, the adversary can compromise users and learn their private state and their password. All of our games model both adaptive and selective compromises. The adversary also has access to a set of oracles that they can use to choose which user performs which operation in which order. Now this you can think of as the interactive oracles that maybe some of you are familiar with from key exchange models. And so one call to such an oracle means that we process the server message that's chosen by the adversary, and then the oracle will output the honest user's message in this protocol run, which is the next message in an interactive protocol with multiple messages. And so we formalize two basic security notions, integrity and confidentiality. For the integrity game, the adversary simulates interaction with many users in the way we described before. And it wins if at some point in this interaction, it can serve a malicious file to a user without them noticing. And so this can mean that it either can serve a file that the user never uploaded themselves, or that it can modify a file that the user has uploaded. For the confidentiality game, we give the adversary an additional oracle to which it can provide two files, F0 and F1, of the same length. And then the game will pick one of those files and upload it to the server. This is depending on the game bit B. And the task of the adversary is to guess which file was uploaded, and it wins if it guesses correctly. So this in-CPA-like game might look a bit simple, but keep in mind that this is run while the adversary has access to all oracles, and so it can do any arbitrary interleavings with operations while doing these challenges.
Okay, so let's recap. When we started working on this, end-to-end encrypted cloud storage was an elusive goal. Now we formalize the syntax and security notions, making the goal concrete, namely confidentiality and integrity in the face of a compromised or malicious service provider. And with these security notions, we were able to formally capture the attacks on Mega, showing that they fell short of the goal. So are we done now? Well, no, we're still missing a construction, a cloud storage system which can make it to the goal. So the final contribution of our work that I want to share with you today is our proposal CSS. We were able to show that CSS achieves both confidentiality and integrity, making it the first provably secure end-to-end encrypted cloud storage protocol. So let's take a look at how CSS works. CSS there we go. CSS is built from 4 building blocks: an OPRF, a PRF, an AAD scheme, and a MAC. Except for the OPRF, these are all black box. So the reason that the OPRF is not black box is that we are in the slightly unusual threat model, at least from the OPRF point of view, of a malicious server. So for this reason, the OPRF is instantiated as 2 hash Diffie Hellman, such that we can model the hash functions as random oracles in the security proof. From all of the other building blocks, we only make standard assumptions. Now, in the interest of time, I'm going to simplify the protocols a little bit, and in particular, I'll be leaving out the MAC because it's actually not needed for end-to-end security. So let's take a look at the registration protocol. As all cloud storage protocols, it's an interaction between a client and a server. The client takes as input the user's password and an account ID, which is assumed to be globally unique. So this could be something like an email address or a username. Now, the first thing that the client does is to run an OPRF on input this password and account ID, together with the server key, which is actually sampled on the client. And this is a choice that we made to ensure that the key is honestly generated the first time it's used, since in our threat model, the server is entrusted. Next, the client applies a PRF to the output of the OPRF to generate an AAD key, which we refer to as the key encryption key, or KEK for short. It then samples a uniformly random master key and encrypts this using the KEK to produce the master key envelope. And this key wrapping is done to allow password updates without file tree encryption, as Miro was saying before. Finally, the client sends the account ID, the server's OPRF key, and the master key envelope to the server for storage. The next thing that the client can do is to authenticate or log in. Now, on the simplified level, authentication is actually very similar to registration. The only differences are that the OPRF is now computed together with the server, and that the client decrypts the master key envelope to recover its master key and store it locally. Now, in reality, this protocol is actually a lot more complex. So for example, this is where the MAC comes in to authenticate a session ID exchange, and the session ID is used as a token by the client to authenticate later operations. Now, again, in the interest of time, I'm not going to show you all of the file protocols, but we'll take a look at PUT so that you get a feeling for how files are handled. So to upload a new file to the cloud server, the client will take as input its master key, which is stored locally from authentication, the file content, and a file ID, which is also assumed to be globally unique so that we can implement sharing. To encrypt the file, the client samples a uniformly random file key, and AAD encrypts the file with the file ID as associated data. The file key is then itself encrypted using the master key, also with the file ID as associated data, which binds together these two ciphertexts. Next, the client sends the file ID and the two encrypted the ciphertexts to the server for storage. And on the server, the file ciphertext is stored indexed under the globally unique file ID because this ciphertext is actually shared by all users who have access to the file. In contrast, the file key ciphertext is stored indexed under both the account ID of the user and the file ID because this ciphertext differs for every user. Okay, so let's recap again. We now have syntax, security notions, and a provably secure construction. So are we done now? Well, unfortunately not. At this stage, CSS is just a theoretical construction. We still don't have an implementation or a deployment. So there's still a lot of work to be done to bridge the gap between theory and practice for end-to-end encrypted cloud storage. And we actually need help from both sides. So for example, we were only able to show that CSS is selectively secure due to commitment issues that arise because of the key hierarchy. So if you're a theoretician, we would love your help with an adaptive security proof for CSS. And if you're more of a practical type, well, we'd also like your help to implement or build CSS so that we can bring it to life. From both sides, we'd be happy to hear your feedback and also to see extensions and improvements to our model. If you're interested in more open questions and future work, you can find it in the full version of our paper, which is on ePrint. And with that, I want to say thank you for your attention, and we're happy to try to answer any questions.
Thank you. We have time for one question. There.
Go ahead. Thanks. So what happens, I noticed you use an OPRF to derive the root key. What happens if you use, for example, a just password hashing function instead? What happens if you remove the OPRF from the scheme?
So I think we wanted to increase the strength, basically. So an OPRF is a very good way of hardening a user's password. If you directly extract from the password, you can't get better security than just the password. But by doing this generation on the client of an actual cryptographic key, which is used together with the password in an OPRF, we can actually get better security than we could get from only the password. Then, of course, we outsource this this key to the server, so it's maybe not stronger in the malicious server setting, but we're also trying to target a client to server setting where we're concerned with external adversaries.
Okay.
That doesn't come to the front in our security notions here, but it's something that we're working on showing as well.
Okay, thank you.
And we have one more question.
As far as the implementation goes, I guess I think my starting point would be go talk to these cloud companies and see what they think of the scheme. I wonder if you've reached out to them like, hey, this is the issue we found in your system, and here's how you might do it better. What do you think?
So we have not reached out to the companies that we at least were involved in breaking from the smaller providers, but we have tried to reach out to companies, to the bigger providers that are already having end-to-end encryption or slowly starting to roll it out to see what they think of the scheme, and hopefully to also get feedback from them on scalability issues and practical considerations. But if you can connect us further, I mean, that would be extremely welcome.
I can't. But yeah, having an implementation to start with would probably help a lot. So yeah, great talk. Thank you.
Okay, thank you. So now we are at the third talk of the session. It's about compact key storage. It's joint work by Evgeny Dodis, Daniel Yost, and Antonio Marcedone. And Daniel is giving the talk.
Okay, thanks for the introduction. So the setting of this talk is cloud backup, and the premise is sort of all those nice, really secure apps like Signal, MLS, Zoom, like a lot of end-to-end secure apps. But at the end of the day, users unfortunately don't just want security. Somehow it seems that they can also get quite angry if they lose their data. So it seems that actually we want to have some backup in addition to just security. And it would be even greater if that backup process wouldn't just undermine the entire security we worked so hard on the protocol level to achieve. So what we need is that the applications, in addition, offer a secure backup process in addition to their core functionality. So how does that nowadays roughly look? If you have some kind of group messaging, let's say we have 3 parties, and here the roadrunner wants to disseminate a very important message to their friends. So he would use some kind of group messaging scheme, maybe MLS, that uses some kind of symmetric secret, here called S, to encrypt this message, and then this creates a ciphertext. This ciphertext is distributed via some central infrastructure to all the other parties, who then decrypt it. So now, if we add backup, how would that look like? Well, you would take the plain text, you would run a separate backup protocol, probably like that uses some completely independent secret of the application, produce some kind of ciphertext as well, and then upload it to the cloud. So the idea is that as long as you somehow can remember this backup secret, you could recover all your prior messages from just the cloud storage. And importantly, all of the 3 parties or all of the end parties in a larger group messaging chat would do that independently. So in some sense, each of them has their own cloud. Now, some observations. Well, first, most of the existing solutions as this backup secret, they just use some kind of static secret key. So in some sense, this encryption of the plain text for the backup is just a trivial AAD. You use a secret key and then you call it a day, and somehow the academic research focus mostly on, okay, but how would you actually remember that static secret key in case you lose your phone? So for instance, you could derive it from a password or do stuff like this. Second, as I've already alluded to, each user maintains their own backup. So this is quite inefficient in terms of both storage and bandwidth. If you have a large group with a couple of thousand users and each backups the exact same message to probably the same cloud provider, like, couldn't we do better? Then, because they use a static key, they don't get any post-compromise security or forward secrecy, so it seems that the backup schemes don't get the same level of security we normally require from the messaging level. And like a couple of months ago, there was this incident where on iPhone suddenly old erased messages were reappearing, and initially people were sort of wondering whether this had something to do with the iCloud backup. Well, it turned out the answer was no, that was some other bug. But this is somehow to highlight that if you're using a static key, you don't have any forward secrecy. Then if you want to erase old data, maybe some embarrassing message somebody sent you, then you somehow are at the whim of the cloud provider to actually delete that data. And I mean, if you attended the talk in the morning, in the quantum session, you should know that guaranteed secure erasure against a malicious server is only feasible if you have some quantum server. So this is not really practical nowadays. And finally, this whole backup thingy is sort of a very simple thing. There's no advanced functionality, so maybe we can do also better there. So in our work, which we call compact key storage, we revisit this picture. And what we do is first, we only want to have a single cloud, not each user having one. And second, what we said is like, if you do something with MLS or something that has like a shared group secret, then you already have like one ciphertext for each message. Why not just reuse that ciphertext? And then the security of that ciphertext is also the same as you already analyzed as part of your messaging scheme. And instead, let's say our backup scheme is no longer independent of the messaging app, but it actually now backs up the messaging secret. So the secret that you would then later use to decrypt that ciphertext. And to do that, our CKS protocol uses a compact state, and importantly, that state will evolve with each message so that we can actually provide post-compromise security and forward secrecy. And all of the three parties or all of the N parties do this, but importantly, only one party actually needs to upload something to the cloud. So our entire scheme has like constant cloud storage and bandwidth in the number of parties that are involved in a group chat. To maybe give you a bit more of a high-level schematic overview, if you think of this backup process, what really seems to happen is that in the first step, we take like all the messages and somehow compact it down to a really small state. And then as a separate problem, we sort of wonder, okay, now I have this small state on my phone, but what happens if my phone is lost or it somehow somebody drives over with a car or whatever? Like, how could I somehow ensure that users can recover this small secret state based on some information they can remember? So this compaction is sort of considered, in the past, it's been considered trivial, and all the academic work has been focused on this, what people actually call backup process. And there's a lot of cool work, like using hardware security, or maybe using this password protected secret sharing, or the DPays, and lots more, but this is all great. But what we do is sort of say, hey, let's wait a minute, maybe we should have another look at this first part and see whether we cannot come up with a more clever compaction process. So CKS really only tackles the first problem, and the second problem we then say is orthogonal, where you could reuse many of the old protocols, like this hardware-based, the password-protected, or whatever. So CKS in itself doesn't solve like what happens if you lose your phone, but CKS is like this first step in a more clever way. Okay, with that out of the way, let's recap this first part. So CKS, in contrast to a traditional solution, works on application secrets. The entire backup is shared among all the users instead of having the state grow linear in the number of users. It uses a dynamic secret state and will allow nice post-compromise security and forward secrecy. And it also supports some advanced functionality. For instance, some of the schemes support some kind of delegation. Let's say you have a friend who shows up, maybe you want him to give access to part of your chat or whatever, you could delegate part of those application secrets in an efficient manner. And yeah, just to remember, sort of what CKS does is mostly orthogonal to what existing work on backup did. So let's now look at, in the second part, at our actual primitive, this compact key storage. Before I will then, in a third part, introduce our scheme and finally talk about security. And I would say from an academic point of view, the last part, defining security, might actually be the most important one. So if you fall asleep now, then maybe that would be a good time to wake up again. So let's say we have our three parties, and we now just care about backing up those shared symmetric state. Let's ignore the ciphertext. I mean, uploading ciphertext to a cloud, that's trivial. So, and let's make a simplifying assumption that all of the parties have the exact same sequence of secrets they want to back up. In our paper, we actually look at a more general setting where they might only have subsets or they might even disagree, but here let's keep it simple. Let's say everybody has the same secrets. So they get the first secret, then all of them run a local algorithm that sort of injects these secrets into their local state and also creates an update message. But then crucially, we require only one party to actually run the interactive upload algorithm with the server and use this update message to upload something to the server. So all of our algorithms, we model them as fully interactive just because we wanted to formalize the most general notion of compact key storage. But in our actual scheme, stuff will be essentially as non-interactive as it gets, and it will be essentially like one message from user to the server, and then maybe some acknowledgement back, or in some cases like some basic info from the server first, and then one message. But it's like the interaction is just to keep the notion general. But the algorithms have very low round complexity. So we run this update, and after that, the server also has an updated state. And then the second secret comes, we do the same thing, but now maybe this time another party does the upload. So importantly, we want our primitive to work as long as just one party uploads. It could be more. Still should work, but at least one has, and it doesn't always need to be the same one, so that it simplifies. Like if somebody is offline or something, it can be just whoever's online does it, and it should be fine. Okay, then they could do this more and more again until they have outsourced all the keys. And now I should mention that for our notion, we require that their local state is really compact, so sublinear at least. Logarithmic hopefully, and constant at best. But of course the server state grows linearly in the number of secrets you want to outsource, just from a very basic entropy argument. So then we have another algorithm. Let's say Tweety wants to recover one of the old secrets, and then that's just like another interactive algorithm called retrieve. She can input the epoch number and her state to that, run it with the server, and this will eventually output this old secret for that epoch. Now let's say Bugs Bunny also wants to join the group, and Duffy is somehow willing to share at least part of the chat history with Bugs, so he can try to delegate stuff. How does that work? Well, in the first part, Duffy runs what we call a grant algorithm with the server, and this generates some message which we then distribute out of band. So this out of band is just any kind of secure channel. I mean, if this message gets leaked, then everything Duffy wants to send to Bugs Bunny would be leaked. But other than that, this is very, very, very general. We don't really say what we need from this channel. Just somehow securely give this message to Bugs. Afterwards, Bugs runs another interactive algorithm called accept, and at the end of this, Bugs Bunny will have his own local state, which will allow him to retrieve all the keys for which he has been granted access to. And finally, for some of the schemes, there's an erasure, so you can get forward secrecy, and yeah, that's just another interactive algorithm where you say what you want to erase, and it updates your local state. Nothing too surprising here, I hope. So what are the properties we want of a CKS scheme? First, we obviously want some kind of correctness. What does correctness mean? It means that if an honest user interacts with an honest server, then they should get their old secrets back. And if you have your old secrets and your old ciphertext, then you can use that to get your old plaintext, and everything should work out. I should mention here that we actually formalize some kind of robust correctness property where we say that even if some of the users in the system behave maliciously, run these interactive algorithms as a malicious entity, then this should not screw over the honest users as long as the server behaves honestly. Otherwise, our system would probably not be practical at all if one user in the entire system could just do a denial of service against everybody that will ever use Signal or whatever. Then secondly, we have an integrity property game which looks at, okay, that's a typo, that should say honest user interacting with a malicious server. And this guarantees that if an honest user interacts with a server that might or might not be malicious, then either they get the correct key back or they get an explicit error, but they're never fooled into accepting something that they didn't initially outsource. So in our notion, we do allow for denial of service attacks, so we have these explicit errors. If you want, you could augment our whole primitive with some kind of proof of retrievability. I don't think that in practice anybody actually does this, and if you're using cloud storage, you normally just assume that information isn't deleted, but you could do it. Then finally, there's of course security, and sort of the intuitive thing we want here is that running a CKS scheme does not undermine the security of your secure messaging scheme, of your MLS, of your Signal, of your Zoom, of your whatever. And this is actually quite tricky to formalize, which is why I will now first present the scheme and then talk, if time permits, talk a bit more about security at the end. Okay, so how does our scheme look like? We actually, in our paper, have two schemes for two slightly different settings. One of them we call an all or nothing scheme, and there the setting is really, we do make the simplifying assumption that all users have the same secrets, and all of them. For instance, if you're using something like Slack, there all the users get access to the entire history of message, even if you've been added later, so that would be an application where this scheme would be applicable. If you have some kind of your regular group chat where a party that's added later only has like a new message, then you would use our what we call an interval scheme, and that's applicable if in settings where users only know certain subsets of the secrets. And subset here should have some kind of asterisk, so what we really mean by subset is some kind of union of intervals for a small number of unions, like everything will grow in the number of intervals you locally have information for. What kind of functionality do those two schemes support? The first one just supports delegating prefixes, so either the entire history or like 1 to I, where I is some prefix, some smaller number than your current one. Whereas the interval scheme, given the name, really allows you to delegate arbitrary intervals efficiently. Then the first one has no non-trivial erasure. All you could do is just delete everything and lose access to everything. Whereas in the second one, you can erase efficiently access to like one interval at a time, but the catch here is sort of that with each such erasure operation, your local state grows. So if you have some kind of application where you assume that users either only very infrequently delete stuff, or if you have some kind of automatic erasure after 2 weeks, I think that's fine, because in both cases, what you keep is essentially efficiently representable by an interval. But if you have some kind of degenerated setting where some kind of weird user wants to keep all the odd messages while deleting all the even ones, then our scheme would be inefficient. But it's actually quite easy to see that if you want to support arbitrary subsets, it's impossible to do anything efficient. So I think interval is a very practical compromise. Then finally, in terms of state size, the all or nothing scheme has constant state, the interval scheme has logarithmic state. Key retrieval in the all or nothing scheme takes linear time in contrast, whereas in the interval scheme, everything is logarithmic. So in terms of crypto, the two schemes are actually very, very similar. It's just like you shuffle a bit and arrange it a bit differently. So for the sake of time, in this talk, I will just focus on the simpler of the two schemes, the all or nothing, which contains sort of all the, okay. Yeah, sorry, that was somehow very badly practiced. So let me just skip this. So the one main message is it's built from what's called convergent encryption. You essentially encrypt under a key that you derive from the message itself. This is secure in the random oracle model. Proving that was a bit difficult. And for defining security, what was done naively is impossible. There's an impossibility proof. There are a bunch of alternatives. They don't really work. We try to do the most general stuff. It's a really nice idea. Talk to me in the break if you want to learn more. I think it has applications beyond just backup this type of security scheme. Okay, sorry for running over time.
So, any question? Okay, so let's thank Daniel and all the other speakers of the session.